So since we need the voltage conversion ratio, which is a ratio between the output and input in DC, we need to find an expression for the output voltage, time domain expression. And to find an expression for the output voltage, we can analyze this switched circuit that has two states, one state when S1 is on and the other state when S2 is on. And then let's apply KCL at this node. This is the inductor current IL. And the current here is basically the capacitor current, which is D times the first derivative of the voltage across the capacitor, which is output voltage divided by dt. And the current in the load resistor, which is the output voltage divided by the resistor R. So if we apply KCL here, we have one current entering IL and two currents leaving, the capacitor current and the output current. And then we can rearrange the terms essentially, and we'll get this first order differential equation. And what we are trying to get is the voltage conversion ratio, which is the ratio between the output voltage and input voltage. And to do that, we need to find an expression, a time domain expression for the output voltage. But as you can see in this equation, the only issue we have is we have V out in this term and in this term, but then we have IL. So we need to express the inductor current in terms as a function of V out, so that we have one equation in one unknown, one differential equation, one unknown, which is output voltage, and get expression for it so that we get the conversion ratio. So how to get the an expression for the inductor current? We can say we have two states, so we need to get an expression for the inductor current in state 1 when S1 is on, and then another expression or another equation when S2 is on. Let's take the case when S1 is on. We can apply KVL around this loop, and we can find that the voltage across the inductor is equal to the input voltage minus the output voltage. And so the first derivative of the inductor current is equal to Vn minus V out. And so we get this equation, and then we can use equation 2 in 1 after we take the first derivative of this equation. First, we need to take first derivative of this equation so that instead of IL, we get DIL by dt. Just normal differential equation solution. So we'll get the second derivative of the output voltage, and then 1 over C is the first derivative of the output voltage. Then we have the IL, the first derivative of IL over C, and from that essentially we get this second order differential equation. And that's for state 1, or let's call it state means phase, network phase. So network phase 1 or phase 1, state 1. Then we need to express the voltage across the inductor in state 2 when this switch is on and this switch is open. So essentially we don't have Vn, and so the voltage will equal to minus V out. And then we get another second order differential equation, and then we take these two second order differential equations and jointly solve them together in order to get an expression for the output voltage versus time, and this way we can get the conversion ratio of the power converter. However, this is very involved. There is a much easier way to get the conversion ratio in a simpler way if we use something called small ripple approximation. And after we apply small ripple approximation, we're going to use the volt-second balance principle for an inductor, and both of these, the approximation along with the principle of volt-second balance, will enable us to get the voltage conversion ratio of any DC to DC converters without solving complicated differential equation. So first of all, what is a small ripple approximation? Well, if you are designing a buck converter, you want the output to be very constant. So the output, of course, has some ripple, as you can see here. It's not pure constant DC. But this the peak-to-peak value of this ripple is supposed to be less than 1% of its DC component. And so if we say the output voltage is a DC component V out, in addition to the higher order harmonics or the ripple, these harmonics peak-to-peak value in time domain should be less than 1% of its DC component. So the small ripple approximation, as the name suggests, essentially assumes the ripple is negligible. And so the output is just a pure DC V out. And once we have that, we'll find that it's going to be much easier, much simpler to solve to solve for the inductor current, because now the inductor current, when we get an equation for the inductor current, we said that the voltage across the inductor, if in state 1 or phase 1, is equal to the input voltage minus the output voltage. But the output voltage, as you can see here, is a function of time. So now we can replace this function of time. There is no ripple here from small ripple approximation, so it's just DC. So essentially it's a constant time versus time. And now it's very easy to get an expression for the inductor current, and from the inductor current in a steady state, along with the inductor volt-second balance principle, we'll be able to get the conversion ratio. So that's the first step. Use a small ripple approximation to avoid complicated differential equation or solving joint high order differential equation coupled together, since we have two switching states in this case. And then let's assume that we need to find the inductor current, because obviously it's very easy to find a time domain expression for the inductor current. That's a first order differential equation. This is constant, V out is constant after using the small ripple approximation. So to get the inductor current, first I'm going to get the voltage across the inductor when S1 is on. So S1 is here, and then when S2 is on. When S1 is on, we call it phase 1. When S2 is on, we call it phase 2. So during phase 1, it's obvious, as I mentioned before, the voltage across the inductor is going to be the input voltage minus the output voltage. So this means the first derivative of the inductor current multiplied by inductance is equal to Vn minus Vout. Okay. And then in second phase, phase 2, the voltage across the inductor will be equal to minus Vout. And so if we sketch this is the voltage across the inductor on the y-axis, this is time. The voltage across the inductor in the first phase is Vn minus Vout. In the second phase is going to be minus Vout. That's the first step. We got the voltage across the inductor. After we got the voltage across the inductor, the voltage of an inductor is equal to its first derivative current, or the first derivative of its current is equal to voltage. So once we get the voltage, we can easily get the current, but we are not going to get an equation for it. We're going to sketch it. And that's a good thing about power electronics. We always try to solve everything in a very easy and intuitive way. Okay, so we got the voltage. As you can see, in phase 1, it's a constant number versus time. In phase 2, it's also a constant. If you have a function and its first derivative is equal to a constant, then this function is a straight line. Correct? Because the first derivative of a straight line is going to be a constant. So during the first phase, the constant is positive, and second phase is going to be negative. So we can expect that the inductor current in the first phase is going to be straight line. In the second phase, it will be straight line. In the first phase, since the constant is positive, this means the slope of the line is positive, and so it's going to be a straight line increasing. In the second phase, because the constant is negative, then it will be a decreasing line, a line that with a negative slope, right? So we expect something like that, as shown here. The inductor current will look like that. So now, let's consider as a case of startup of a buck converter. We found a waveform for the inductor current. Remember, what we are trying to get here is an expression for the voltage conversion ratio of the buck converter from the time domain analysis. We tried to get first an expression for the output voltage versus time, but to find that we need to jointly solve two second order differential equations together to get an expression for the output voltage, which is not easy. So we used the small ripple approximation. We got output voltage out of the equation. Now the second state variable in the converter, if you are familiar with state variables of control systems, but anyways, the second state variable is the inductor current. So we got a waveform, you can say an equation, but now at least we know the waveform of the inductor current, and from this way, inductor current will be able to reach a condition from which we get the output voltage or the conversion ratio of the buck converter. So let's consider the case of startup of a buck converter. and this is the current in the inductor. So initially, the voltage, the output voltage, is going to be 0. And so when S1 is on, the inductor current is going to increase from 0 to a specific value during the first phase of the first cycle. And then in the second phase of the first cycle, the inductor current is going to decrease, as we know, but with a very small slope, because in this case, dIL by dt is equal to minus almost 0, a very small negative value, so it will almost stay constant or decrease a little bit. But after the first cycle, the output voltage has increased a little bit, and so there's some voltage here. And then in the first phase of the second phase, the inductor current will increase, but with a less steep slope, with a smaller slope, not as steep as it was in the first step, but in the second step is going to be less steep, and that's because now there is some voltage across the inductor, and the inductor current slope will be Vn a smaller value, rather than in this case it was Vn over L, where the voltage is almost 0. And so on, this will repeat, and we'll find that in the second phase of the second cycle, the inductor current is going to decrease with a steeper slope than the second phase of the first cycle, because here there is some output voltage value that's higher in value than it was in the first cycle. So this is the output voltage in the second cycle. This is the output voltage in the first cycle. It's smaller, and so the slope here is less steep than the slope here, and so on. So you'll notice that the slope of the inductor current in the first phase decreases with time, while the slope of the inductor current in the second phase is becoming more steep, until at some point the increase in the inductor current during the first phase is equal to the decrease in the inductor current in the second phase. And that's what's called steady state. This is when the converter reaches steady, when the increase in the inductor current in the first phase is equal to the decrease in the inductor current in the second phase. That's when the converter has reached steady state. And the reason for that is, if the increase in the inductor current in the first phase is higher than the decrease in the second phase, then essentially, I said, if the increase in the inductor current in the first phase is higher than the decrease in the inductor current in the second phase, this inductor current increases to infinity, and the converter will blow up. That's not steady state. That's not a valid steady state. On the other hand, if the increase in the decrease in the inductor current in the second phase is larger than the increase in the first phase, then the inductor current will decrease until it reaches 0, which is also not a valid steady state. The only valid steady state is when the increase in the inductor current in the first phase is equal to the decrease in the inductor current in the second phase. And from this simple observation, otherwise we are in transient, not in steady state. So the only way to reach a steady state is when the increase in the inductor current in the first phase is equal to the decrease in the inductor current in the second phase, and that's essentially what's called inductor volt second balance principle. So the increase of the inductor current in the first phase is equal to decrease. The increase here, this value from the triangle, is equal to the slope of this line, which is equal to, let me write here, Vn minus Vr divided by L, that's the slope, times this duration to get the y dimensions, is the increase in the inductor current during the first phase, which is equal to dt, is equal to the decrease in absolute value. The slope of this line is negative, but let's take its absolute value, and is equal to V out divided by L times this interval, which is 1 t. If you simplify this equation, you will find that you will reach the equation that the output voltage is equal to the duty cycle times Vn, which we reached before using frequency domain analysis. And so the conversion ratio of the buck converter is equal to D. And that's how to get the conversion ratio of a DC to DC converter in time domain, by using the inductor volt second balance principle, which states that in steady state the increase in the inductor current must equal the decrease in its value in the inductor current. And by the way, this condition, another way to state the inductor volt second balance principle is via the integration of the voltage across the inductor. So one expression states that In steady state, the increase in the inductor current must equal the decrease in its current. Another way to state it is using this integration, that the integral of the inductor voltage waveform across one complete cycle must equal to 0. How did we reach that? Well, we know that if we the voltage across the inductor equal to di L by dt, but of course we multiply by L. So if we do the other way around, we reach that then IL of T2 minus IL of T1 is equal to the is equal to 1 over L, the integral of the inductor voltage dt from T1 to T2. So now if we make the signal periodic, if we say this is T1, this is T1, and this is I of T1, and then let's take a complete cycle. So if we take one complete cycle from T1, then we reach this point, and the current here is exactly equal to the current at IT1. So I at T1 plus T is equal to I at T1. And so essentially from the integral, if we say integral equation for the inductor, I T1 plus T is minus I of T1 is equal to 1 over L integration of from T1 to T1 plus T VL of T dt. We know that IT1 must equal to IT1 plus T under periodic operation or under a valid steady state. So essentially this integration will equal to 0, and so we can cancel L and we get this equation that in steady state, the integral of the voltage across the inductor across or over a complete cycle must equal to 0 under a steady state or under a valid steady state. By the way, the integration of the voltage across the inductor is basically what? Is the area under VL, under the voltage across the inductor. So this means that the total area under the voltage across the inductor over a complete cycle must equal 0. And when I say that, this means that all of this so this is a voltage across the inductor and a buck converter. So this is the it has a positive voltage, or this rectangular area must equal this rectangular area that's negative, so that both areas, the total area across the inductor voltage waveform of the inductor across or over one complete cycle is equal to 0. Another conclusion of this fact, which is another way to state the inductor volt second balance principle, if we have a converter under steady state operation, we can expect that any inductor inside this converter will have a voltage across one cycle or across a complete cycle will have some positive parts and some negative parts. It cannot be all positive in one cycle. This means it's not steady state, because under steady state the inductor volt second balance principle applies, and if it's all positive, then the total area across the voltage across the inductor will not be 0. It has to have some negative parts and positive parts so that they cancel each other, and the total area across a complete cycle is 0. Okay. A third conclusion from this equation or this expression of the inductor volt second balance, essentially the units of this is going to be volt times second. And volt times second, that's essentially the unit for flux. That's why the volt second balance principle is also called the flux balance principle. And so to conclude, the approach to get the voltage conversion ratio of a power converter, buck converter, boost, any other converter, buck boost, whatever we're going to see, is very simple. The first, in time domain, the first thing, we're going to sketch the voltage across the inductor over a complete cycle. And then we'll apply the principle of inductor volt second balance, which states that simply that the total area under the inductor voltage is over one complete cycle is equal to 0, or essentially over one cycle the positive area under the inductor voltage is going to equal the negative area. And from this condition, which is from here, we can get the voltage conversion ratio of a power converter.